Today we're going to take a peek at exponential functions, and we're going to take a look at how to graph them as well as how to solve some of them. So we start out with basically a parent function, and our parent function is an exponential of the form cx to the a. All exponentials will be of this form, and this is your basic function where your base value, 3 is a base, we call that a is equal to the base, and then your exponent x is obviously your variable, outputs y. So what I like to do on these is I just, first time through, I'll take and plug and chug. So let's pick some positives like 0, 1, and 2, and some negatives like 0 or negative 1 and negative 2. So plug in 2, 3 squared is 9, plug in 1, 3 to the first is 3, plug in 0, anything to the 0 power is 1. 3 to the negative 1, that's like taking the reciprocal, so that's 1/3, and then finally 1/9. So if I go ahead and graph those, here's 0, 1, 0, 3, 6, 9, 1/3, 1/9. So you can see this exponential function rises quite quickly, like so, and it levels out. What power of a positive number will ever equal a negative number? None. So what happens in all of these exponentials is we're going to get some horizontal asymptote. And in this case, our asymptote is at y equals 0. Now, the range for this and the domain for this we can see by just looking at the graph. You notice that the blue line will go on forever to the left, and in theory, even though it's going up very high, it continues to move over to the right as well. So your domain for these is all reals. And then the range, this never goes below this horizontal axis of y equals 0, and it'll never actually touch y equals 0 either. So our range is y is greater than 0. Let's move on to the next. So we've already gone through our transformations, and a f of x minus h over b plus k. This works for any kind of function, including these exponentials. So we notice here, negative 5 is our h value, and our k value is negative 2. Which means this moves over and down. So what I'm going to do is move over 5, 1, 2, 3, 4, 5, down 2, and I'm going to create this fictional set of axes here. And then I'm going to graph my parent function, since there is no a value. I'm going to graph my parent function from that point. And my parent function is just 2 to the x. So if I take a look at some values here, negative 2, negative 1, 0, 1, and 2, I know that at 2 I have 4, 2, 1, 1/2, 1/4. And I'll do all that graphing from this new point down here. So 0, 1 puts me at this point, 1, 2 puts me at this point, 2, 4 up here, negative 1.5, negative 1.25. And I'm going to go through and just make sure I check this as well. So I'm going to pick an actual point somewhere on this graph. This is a good one right here. It's easy to see, so it's negative 3 and 2. And I'll plug it into this function here to make sure it works. So I have 2 to the negative 3 plus 5 power minus 2. So this is 2 squared, which is 4, minus 2 is equal to 2, and that checks. So I've done it correctly. Now let's look at the domain and range. Again, this seems to take and move all the way to the left, and it keeps going to the right, so this will be all reals again. Before I do the range, let's take a look at an asymptote. You can see that it'll never go below this dotted line here. So it appears my asymptote is at y equals -2. And my range is always above that. So y is greater than -2 will be my range. Let's take a look at another one. Now, there's a special constant in math, and that constant's called E. It's called the natural base. And it has a value of approximately 2.718. And they use it sometimes kind of just like they would use pi, but in terms of exponential problems. Then we'll show you where this comes in later. So if I wanted to graph negative e to the x minus 3, this again is going to be somewhat of an estimation because we've got this ugly decimal right here. But let's go through a couple of things. We know that there's an h value of 3 in this case. So we'll make h equal to 3. And we know we have an a value in this case. It's out in front. A is equal to -1. So we're going to multiply y by -1. All right? So once we've identified these values, we're going to take and graph the parent function of y equals e to the x. Again, use small numbers like -2, -1, 0, 1, and 2. And you may need a little help from your calculator to get these, which kind of defeats the purpose of graphing these. We plug in a 0, anything to the 0 power is 1. We do that. E to the first is 2.71. E to the second is around 7.38-ish. E to the -1 is about 0.36. Again, I'm using my calculator, not just pulling these out of midair. And 0.13 is e to the -2. So we're going to graph these from my new origin, if you will. So my origin in this case is 3 over. So I'll move over 3, draw this fictional set of axes, and then take and plot these points from here. So 0, 1, once again, 1 and about 2.7, right around here, 2 over, and 7.1 up, roughly right around here. 0.3 is at -1, roughly there, and 0.1 is at -2. So again, you'll notice this exponential shape rising very quickly and having some form of an asymptote, which appears to be at the x-axis, which it is. Domains all reals, so we're noticing a pattern here. Range is y is greater than or equal to 0. And you'll notice I haven't finished this problem because I didn't go and multiply by -1. So let's do that. This goes to -0.13, -0.36, -1, -2.71, and -7.38. So that takes this blue graph and basically flips it upside down. So we go here, here, and it's 3, 1, 2, 3, roughly here, here, and here. So the red graph is actually going to be our final answer. Sorry to take you on a quick detour. So instead of our range being y is greater than 0, it's actually y is less than or equal to 0. And our horizontal asymptote is still going to be y equals 0. Alright, now we're going to solve some exponentials. Let's look at a basic example. If I have something like 2 to the x is equal to 2 to the 7th, I'm not trying to insult your intelligence, but what would be the x value? Well, if these base values are the same, 2 and 2, then these exponents would have to be equal. So x obviously would equal 7 in this case. Same principle here, my two base values are the same, but I have different exponents. Well, if this is going to be 5 to some power and we have two unknown powers, but the quantities have to be equal, then these powers must be equal. So I can basically drop the bases out and set x plus 1 equal to 6x plus 11. Again, this is only when your base values are the same. So I solve and I get 5x equals negative 10, and negative 2 is equal to x. So now in the next two cases, our base values aren't the same. However, we can make one of these numbers look like the other without changing its value. Now a lot of people will always go, well, 3 squared is 9. But if I make this 3 squared, I'm changing the value of 3. Whereas if I say, well, hey, 9 is 3 squared, I haven't changed the value of 9. And that's raised to the x plus 1 is equal to 3 to the 4x plus 5. Now I have properties of exponents that say if I have a power raised to a power, I can multiply those powers. So this is just 3 to the 2x plus 2 is equal to 3 to the 4x plus 5. And now you'll notice my bases are the same, so I can drop the bases out and set the two powers equal to each other and go ahead and solve that simple linear equation. So I have 2x equaling negative 3, and negative 3 halves is going to be equal to x. Likewise over here, I'm going to try to make one of these look like another, or maybe both of them look like something else, which is the case in this situation. 4 is easily expressed as a power of 2, that's just 2 squared, and that's raised to the 2x power. If I want to make 1/2 a power of 2, that's simply 2 to the negative 1 power. Remember, those negative powers take the reciprocal of its base. So that's to the 1 minus 2x power. Again, I have power quantities raised to another power, so I'm going to multiply powers. That's 2 to the 4x is equal to 2 to the 2x minus 1, distributing the negative 1 through. Again, I can drop the bases out, so that's 4x equals 2x minus 1, 2x equals negative 1, and x is equal to negative 1/2. Alright, so the next thing we're going to do is we're going to determine if we've got a linear or an exponential pattern. Alright, and it's basically the case that if the rate of change, which means the slope, right, we know that, if the slope from point to point is constant, it's linear. If the ratio of consecutive outputs, this is new, is constant, then it's an exponential function. So let's take a look and calculate the slope from point to point. I'll put m right here. So the slope in this case, between these two numbers, we're going to take the difference of y's minus the difference of x's. So in this case, we have 2 over 2, which is equal to 1. Find the slope in this case, 2 over 2, which is 1. This case, 2 over 2, which is 1. And in this case, 2 over 2, which is 1. So this appears to have a constant slope. And when we have a constant slope, we know that this is a linear function. Or constant rate of change. And if I were to graph those things, you could easily see, kind of with the naked eye, that that's going to be the case. Something of this nature. So it's going to appear to rise like this. Now, again, looking at the naked eye of this chart here, we'll see this appears to not be linear. If I go 0, 3, 1, 6, 2, 12, 4, 48, it's off the page. It appears to be rising quite sharply. So it could be exponential, but we have to make sure that this ratio of constant or consecutive outputs is constant. Let's go through and calculate slopes first. M is basically 3 over 1. The slope here is 6 over 1. So that's equal to 3, 6. Slope here is 12 over 1. So we got 12, etc., etc., etc. This guy is going to be 24 over 1, which is 24. Now, when we talk about consecutive output ratios, ratio consecutive, right? We're going to basically take and find the ratio of all the y's to each other. So in this case, what I have is I have 6 over 3 for the first one, which is 2. 12 over 6 for the second one, which is 2. 24 over 12 for the third one, which is 2. 48 over 24 for the next one, which is 2. And you can see that the ratio of consecutive outputs being y, is constant. So this is exponential. And that's how you tell if something's linear or exponential as far as their pattern goes without having to graph it. So that should get you through today's lesson. And do your Mind Math Lab, write the summary, and we'll talk about this more tomorrow.